Okay, welcome to this video lecture series for EE320. So I am right now in sunny California. It is, I'm going to guess about 77 degrees, so very pleasant here. I hope you're enjoying your time learning about instrumentation amplifiers. The things you learn here today will absolutely be things you use further on in your career. When I say absolutely, I mean most likely. When I say most likely, I mean probably about half of you. But these are very good things to know regardless. So in our previous discussion about instrumentation amplifiers, we talked about difference amplifiers. We talked about amplifier designs that used one op amp, maybe had a second op amp to achieve some other feature. But one of the things about those difference amplifiers and about the standard difference amplifier is it's non-ideal in the sense that it has a finite input impedance. What we really want from an ideal amplifier is infinite input impedance we'd like to have adjustable gain, and we'd like to have infinite common mode rejection. So essentially what we want in a true ideal difference amplifier is to be able to take the difference between two signals and have zero amplification, total attenuation of the common mode signal. Those two inputs would have close to, as possible, infinite input impedance. And we'd be able to have an adjustable gain for those. And of course, there's frequency parameters, which we don't talk about in this class, but also we'd like to have it work ideally up to an infinite range of frequencies. Of course, we know we can't get there, but how do we get closer? The biggest thing we're missing right now is we have a finite input impedance, finite input resistance. So the circuits that we talked about, the gain was determined by a ratio of resistors. As you know, when we have a ratio of resistors creating gain, those resistors can't just be impossibly large. We can't have a 10 gig ohm resistor. We can't have a 1 gig ohm resistor and use those. Why? As we've talked about, one of the problems with those large resistors is, one, if we're using a shunt topology, those large resistors mean we have a very low or very high feedback attenuation in the feedback path, which has negative consequences. Also because working with those massive resistances, even very small straight capacitances can create RC time constants that we don't want. And again, those are mostly things that show up when we start dealing with signals with a certain frequency component, but it's still, the basic idea is we can't use resistors of unlimited resistance. And for practical purposes, we tend to keep resistors under about 100 kilo ohms, under a mega ohm or so if we're using a better amplifier, we know we can get away with it. But how can we build a difference amplifier that does have infinite input, or as close to infinite input impedance as we can get? We've talked about amplifiers that have very high input impedance, and how do we get that? So pause the video, talk amongst yourselves about how you achieve very high input, or how you would achieve, if you were designing a difference amplifier, how you would achieve very high input resistance. All right, welcome back to the video. So hopefully you came up with the basic approach to getting very high input resistance is to buffer our inputs. So if we have a standard op amp buffer, so the input to this is going to be into the gate of that op amp, which with certain types of op amps, especially with op amps that have a JFET input stage or a MOSFET input stage, this input resistance can be extremely high. It's not, of course, going to be infinite, but it can be on the order of giga-ohms or even tera-ohms sometimes. So we can get very high input impedances. So how would we then build a difference amplifier with buffered inputs? Well, what I'm going to do is I'm going to first draw the circuit on the board, and then we're going to sort of talk about the behavior. And as we talk about the behavior, I'm going to have parts of the video. I'm going to have you solve for you take a crack at solving for some element of the design, and then we'll come back and I'll sort of fill in the gaps. So, first of all, let's draw the high input impedance buffered difference amplifier, which is sometimes called, it's a triple op-amp instrumentation amplifier. Okay. So this op-amp, this side of this op-amp design should be fairly familiar to you. So this side of the amplifier is going to be a standard difference amplifier. And then over here we have these basically buffered inputs. Now the question, what's really unique about this is what's going on here. So this is where some of the most interesting math happens. So what I want you to do right now is don't worry about this side of the circuit at all. So don't worry about anything that's going on over here. Just look at this side of the circuit and try to find an expression for V out 1 and V out 2. Specifically for the difference, for this difference, V out 1 minus V out 2. And while you're doing that, you can pause the video. So try to find this expression. You can pause it. I'm going to step back to the camera and make sure everything's still looking pretty good. And all right, so take a crack at this. Try to find this V out V1. And as a little hint, remember, you should know the voltages here and here as a hint for how to solve this. Okay, and you can use ideal amplifier assumptions for this problem. Okay, good luck. Okay, and it still looked like it's visible on the video. There might be a little glare. I hope it's not too bad for you. I hope you can see it zoomed in. Okay, so let's start our analysis of this circuit. So if we assume these op-amps are doing their job, the voltage at this negative terminal should be V2, and the voltage at this negative terminal should be V1. So that means the voltage here is V1 and V2. And it allows us to solve for the current flowing through this resistor, RG. So the current flowing through this resistor, we'll call it just IG. This current, IG, is just going to be V1 minus V2 divided by RG. But what else can we say about that current? That current is also the current flowing through here and here. Why do we know that's the case? That's right, we know that's the case because in the ideal assumption, in the ideal amplifier assumption, we have no current flowing in here or current flowing in here, which means by Kirchhoff's current law, whatever current flows through this resistor has to flow through this, and whatever current flows through this resistor also has to flow through here. So that means that this voltage difference here, this voltage difference is going to be produced by this known current IG flowing through all three of these resistors in series. Therefore, this voltage, V out 1 minus V out 2, is going to be the current, which is V1 minus V2 over RG, times this resistance, the sum of this resistance, which is going to be R3 plus R3 plus RG. So what has this done for us now? So what we have is we have, in fact, this output voltage differential, which is the difference between these two input voltages. And it is scaled by this factor, R3 plus R3 plus RG divided by RG. Sorry, divided by RG. So what this gives us a mechanism by which we can add a little bit of gain to this initial stage. So what we can do is by, let's say for instance, we designed this amplifier and we had initially 100K resistor for R3 and a 100K resistor for R3 here. What resistance value would we need to make an overall gain of this first stage of 100? So again, assuming 100 kilo ohm, 100 kilo ohm, what value of RG do we need to have an overall gain of 100 kilo ohms? So you try that, pause the video, and we'll come back. Okay, so welcome back. So hopefully you noticed, right, that the gain term here for this first stage is just 2R3 plus RG over RG. So if we are saying we want a gain of this initial stage of 100, and we know that R3 was 100K, so 2R3 is going to be 200,000 plus RG over RG, we can simply solve this expression for RG. So I got to give myself a little bit more room here. So we can say 100 RG equals 200K plus RG. Subtracting an RG from both sides, we get 99 RG equals 200K divided by 99 divided by 99. So RG is equal to 1,900. Sorry, I did the math wrong. RG is just equal to whatever. It's going to be about, we'll call it about equal to 2K. Sorry, it's actually going to be a little bit larger than 2K. I went the wrong way for some reason. So it's going to be about equal to 2K. Not quite though. But you see, this gives us, what would happen if we make this RG larger, right? The larger RG gets, the smaller our overall gain will be in this system. And the smaller RG gets, the larger the overall gain will be. And that makes sense, of course, because RG is what determines this current, and then it is these fixed resistors, which were fairly large at 100K, that provided that overall voltage gain. But the nice thing about this, about doing an initial stage of the amplifier like this RG here is a component that, if varied, will change the overall pre-gain of the amplifier. What that can allow us to do is we can keep, if we are building this amplifier as a monolithic IC chip, we can keep R1 and R2 as permanent values that are just established within the chip, just resistances within the chip itself. And we can make RG a component that is external to the amplifier design. So this is a component, the user would have to provide one resistance, RG, and that RG could be used to program the overall gain of the amplifier. And this is actually the way these work. If you look at common, this would be called an instrumentation amplifier. If you look at almost all of them will have this RG as something that you have to provide to the chip. So you have to provide a resistive connection between two terminals of the chip with a resistor RG, and that RG sets the overall gain. And usually what's going to happen with these chips as well is we're not just going to have the gain from this initial stage, we're also going to have typically a little bit of built-in gain at the second stage. Usually you don't want to have all your gain at one. You get better performance if you balance the gain stages. And that's usually what happens. And so in that case, we'd have to look at the data sheet for the part, and we would have to see, there'd probably be some table for the overall gain based on values for RG. And in this case, I chose a value that was I chose, oh, sorry, we get sort of a not super clean, it's going to be slightly over 2K gain here. Usually what they'll do when they actually design these is they would design, instead of these resistors being 100K, they'd be something like 99.5, or they'd pick a value so that we can have kind of cleaner values line up to get sort of an easier to understand relationship between the value of RG and the overall gain of the amplifier. Okay. So, you know from I'm going to stop the video here for a sec, and then we'll come back. Thank you.